Not a wall of brick or stone, but a wall made of galaxies, stretched across 3 billion light-years of empty space, and it is not supposed to exist. Two of the most powerful observatories ever built, on 2 different continents, pointed at 2 different patches of sky, using 2 completely different methods, and they both ran into the same thing. Neither team was looking for it. Both of them found it anyway. And right now, a small group of physicists is quietly asking a question that sounds almost too big to say out loud. What if the universe does not look the way we have always assumed it does? This is not a fringe claim from some obscure blog. It is a peer-reviewed study published this year in the journal Nature, built on the largest 3-dimensional map of the universe ever assembled. The map comes from the Dark Energy Spectroscopic Instrument, known as DESI, a survey based in Arizona that has already reshaped how cosmologists think about the cosmos. The new analysis was done by Francesco Silos Labini of the Enrico Fermi Research Center in Rome and Marco Galoppo of the University of Canterbury in New Zealand, at the same time on a completely separate project, a team led by researchers at the University of California. Riverside used the James Webb Space Telescope to build the most detailed map ever made of what astronomers call the cosmic web. 2 teams, 2 instruments, 2 methods that do not talk to each other. And now a 3rd observatory, the Vera C. Rubin Observatory in Chile, is about to weigh in with a 10-year survey built specifically to settle the question once and for all. Here's the part that makes this worth sitting with for a second. Imagine the universe as a sponge if you sliced it open and looked inside. There are dense, tangled ridges where the material is thick, and there are big empty pockets in between. Cosmologists call that sponge-like architecture the cosmic web, and it is made of dark matter, gas, and galaxies strung together into filaments and sheets wrapped around vast, nearly empty voids. According to the standard model of cosmology, called lambda cold dark matter, that sponge is supposed to look basically the same no matter which direction you look or which region you zoom into, once you get to a large enough scale. Small clumps and clusters, sure, but zoom out far enough, and it should all smooth out into an even, featureless pattern. That is one of the load, bearing assumptions holding up modern cosmology. And that assumption is exactly what just cracked. To understand how big of a crack we're talking about, you need one number, and it deserves 2 comparisons instead of 1. The structures Silos, Labini, and Galoppo identified persist on the scale of a gigaparsec. A gigaparsec is roughly 3.26 billion light-years. If the diameter of the Milky Way galaxy were shrunk down to the width of a single human hair, a structure on the gigaparsec scale would still stretch the length of 40 football fields laid end to end. Or think of it this way, light left some of the galaxies in these structures before the sun had even finished forming. That is the size of pattern we are talking about, and it is not supposed to be a pattern at all. It is supposed to be noise. Silos, Labini, and Galoppo did not go hunting for controversy. They went looking for a number. Using a statistical tool called the angular distribution of pairwise distances, they combed through DESI's release of the largest high-resolution 3-dimensional map of the universe ever built, released last year, and they measured how galaxies were spread out across enormous volumes of space. What they found were persistent, directional clumps of galaxies. Not random noise smoothing out the way the standard model predicts, but coherent structures, pointing in preferred directions, stretching across gigaparsec scales. In an exchange with 404 Media, the 2 physicists said the structures observed in the real universe are significantly larger and more persistent than anything produced in state-of-the-art simulations built on the standard model. That is where the story would already be strange enough on its own. Galoppo put it plainly in a follow-up call, saying the idea was to actually test whether the assumption that isotropy kicks in at very large scales is genuinely supported by the data we now have. He pointed out that even 5 or 10 years ago, astronomers simply did not have datasets deep enough or wide enough to test anything on the gigaparsec scale. DESI changed that. And Labini added that what their method allowed them to do for the first time was actually characterize how large the largest structures inside that sample really are, instead of just noticing that something looked unusual and moving on. That distinction matters because eyeballing a strange pattern in a scatterplot is one thing. Rigorously measuring its size, its direction, and its statistical significance against thousands of simulated universes is something else entirely. And that is the harder, more careful work the 2 of them actually did, and to be clear about what not supposed to exist really means here. Nobody is saying the standard model predicts a smooth, featureless universe with 0 structure at all. It fully expects filaments, clusters, and voids. What it does not expect is for those directional patterns to stay coherent and pointed the same way across a gigaparsec of space. In the standard picture, once you zoom out far enough, all those preferred directions should wash out into cosmic static, the same way ocean waves eventually blend into a flat horizon from high enough in the air. What Silos, Labini, and Galoppo found instead looks more like waves that keep rolling in the same direction no matter how far out you zoom, which is exactly the kind of thing that should not survive at that scale if the standard assumptions are correct. But here's where it gets interesting, because roughly around the same period, a completely different team, using a completely different telescope, was staring at a completely different problem and walking straight into the same wall. The James Webb Space Telescope's Cosmos Webb survey is the largest JWST survey conducted to date, led by researchers at the University of California, Riverside, including Hossein Hatamnia and his advisor, physics and astronomy professor Bahram Mobasher. The team traced the cosmic web back to a period when the universe was only about 1 billion years old, publishing their results in the Astrophysical Journal. Where DESI measures the position of galaxies scattered across the nearby universe using spectroscopy, Webb was doing something almost opposite, peering incredibly deep into the past, reconstructing the skeleton of the cosmos in infrared light across nearly 14 billion years of cosmic history. Mobasher has said the new data provides a far more detailed view of large-scale cosmic structures than anything Hubble managed to capture before it, with once blurred features now resolved with striking clarity. The Cosmos Webb survey itself is a massive undertaking, drawing on more than 164,000 galaxies to trace how the cosmic web's filaments and voids evolved across nearly the entire history of the universe. What makes this so striking is what the comparison images show. Earlier surveys, including the older Cosmos 2020 catalog, tended to blur dense regions together, overestimating some areas and underestimating the emptiness of others. Webb's infrared sensitivity cut through that blur. In the new map, structures that used to look like a single smudge separate cleanly into distinct filaments, clusters, and voids, giving researchers a genuinely sharper picture of how galaxies clumped together and grew during the universe's so-called cosmic noon, the peak era of star formation billions of years ago. Hatamnia and his colleagues found that in denser regions, galaxies tended to grow fast and early, while in later cosmic epochs, those same dense environments increasingly shut star formation down instead of fueling it. None of that alone screams impossible structure. But the density and reach of what Webb was resolving kept turning out to be greater than the previous generation of instruments had prepared anyone to expect. Now, stack those two findings side by side for a second. One team is looking at galaxies relatively close to us, spread across the largest 3D catalog ever built, and finding structures that are bigger and more stubbornly persistent than any simulation predicted. The other team is looking billions of years into the past, using an entirely different telescope and an entirely different technique, and finding a cosmic web that is richer, denser, and more intricately structured than the earlier generation of surveys ever revealed. Neither discovery by itself proves the other correct, but put together, they are pointing at the same uncomfortable possibility. Whatever built the architecture of the universe, it built something bigger and more coherent than the leading model expects. Let's pause and recap what we've covered before we go further, because this is the part where the story really opens up. So far, we've got a nature study revealing gigaparsec scale, anisotropies inside DESI's galaxy map, a separate James Webb survey revealing an unexpectedly dense and detailed cosmic web reaching back to the universe's first billion years, and both of them landing on something the standard cosmological model did not anticipate. So the obvious next question is this a coincidence, or is there a third observatory that can actually test whether these two things are related? That's exactly where the Vera C Rubin Observatory comes in, and this is the part of the story that turns speculation into an actual experiment. Rubin sits on Cerro Pachon in northern Chile, at an elevation of roughly 2,680 meters, chosen for its dry air and its unusually dark, stable skies. It houses the largest digital camera ever built for astronomy, and it just began its 10-year legacy survey of space and time called LSST, designed to catalog roughly 20 billion galaxies and 17 billion Milky Way stars over the course of a decade. One of Rubin's central science goals is constraining dark energy through something called cosmic shear, essentially measuring how the large-scale structure of the universe bends and warps light as it travels toward us. According to the team behind the nature study, DESI is expected to release a fresh batch of observations within the next year, and similar independent datasets are expected soon from Europe's Euclid Space Telescope and from Rubin itself. In other words, we are not just looking at two lucky coincidences from two unrelated instruments anymore. We are looking at the front edge of an incoming wave of data, specifically built to check whether this impossible structure is real, is a statistical fluke, or is something in between. And the scientists behind the original discovery are being remarkably candid about how significant that would be. Silos Labini and Galapo have said that at present there is no simple or widely accepted modification of the standard cosmological model that naturally explains structures this size while still matching the observed uniformity of the cosmic microwave background, which is the oldest light in the universe and one of cosmology's most trusted yardsticks. That tension between what the oldest light tells us and what the largest galaxy surveys are now finding is precisely why this gap between theory and observation matters so much. If you're wondering why this hasn't already rewritten every physics textbook, that's a fair question, and it deserves an honest answer. So let's slow down for a moment. Right now, we're at roughly the 80% mark of this story, and this is exactly the point where a lot of coverage of exciting science stories starts to blur the line between something real happened and something has been proven. So here's what's actually solid, and here's what isn't. What's solid? DESI's 3D galaxy map is real, peer-reviewed, and enormous. The ADPD statistical method Silos Labini and Galapo used is a legitimate and published technique for quantifying anisotropy, and the paper describing gigaparsec scale structures went through Nature's review process. What's also solid, separately, the James Webb Cosmos Web Survey is real. Its findings on the density and structure of the early cosmic web were published in the Astrophysical Journal, and Bahram Mobasher's team genuinely found more detail in the cosmic web than earlier surveys captured. What is not yet proven is that these two findings describe the exact same physical structure, sitting in the exact same location in space, confirmed by both instruments independently. DESI's anisotropies are a statistical, population-level pattern found across an enormous galaxy catalog. Webb's cosmic web map is a separate population-level reconstruction of structure across cosmic time. Nobody has pointed both telescopes at one identical patch of sky and said, "Here, this exact filament confirmed twice." What we have instead is two independent lines of population-level evidence converging on the same broader conclusion, that the universe's large-scale architecture may be bigger, more persistent, and less uniform than the standard model predicts. That is genuinely significant. It is not yet a single confirmed object that both telescopes photographed together. And Rubin's own dedicated results on this specific question have not been published yet either. Its survey is only just getting underway. To be clear, nobody serious is claiming the standard model of cosmology is being thrown out. What they are saying is that a real measurable discrepancy has shown up in two independent places, and it deserves a serious, sustained look, which is exactly why 3 separate observatories are now converging on the same question. If you're the kind of person who likes sitting with big open questions like this one, this is a good moment to hit subscribe, because the next year or two is going to be genuinely pivotal for this story. With fresh DESI data, Euclid's early results, and Rubin's first full survey year all landing in roughly the same window. So where does that leave us? It leaves us with a universe that, at its very largest scales, might not be behaving quite the way 3 generations of cosmologists were trained to expect. It leaves us with 2 teams, working independently on different continents with different tools, both bumping into the same unexpected wall of structure. And it leaves us with a 3rd observatory, named after the woman who first found solid evidence for dark matter by noticing that galaxies were not moving the way they should, now aimed squarely at the same mystery, ready to tell us within a few years whether this is the beginning of a genuine shift in how we understand the cosmos, or a strange temporary wrinkle that later data smooths back out. Either answer would be remarkable. One confirms that the universe is stranger and more structured than we thought. The other confirms just how good our current model has become at surviving its hardest tests. Before you go, here is the question worth sitting with. Which of the 2 findings struck you as more surprising? The idea that DESI found galaxy structures stretching across 3 billion light-years in a pattern that should not exist, or the idea that James Webb's cosmic web map turned out richer and more detailed than anyone expected from the universe's first billion years? Tell me which one in the comments, and if you want to be here when Rubin's first real results come in, make sure you're subscribed, because this is one of those rare stories where we genuinely do not yet know how it ends.